in honor of March 3, World Wildlife Day, for the very first time. Stay tuned and subscribe.
In the untamed wilderness of North America, one creature embodies raw power and remarkable engineering.
When you watch how it moves, you realize nothing is wasted. Every step has purpose.
It is not just strength that defines the grizzly, but awareness, balance, and control.
When I look into its eyes, I don't just see an animal. I see intelligence shaped by nature.
Size alone does not make it formidable. It is how that mass moves with precision.
Every movement feels deliberate, as if nature refined it over countless years.
Within its calm exterior lies explosive power, released only when needed.
It's not just strength, it's timing, instinct, and harmony with its world.
To understand its design, we must first learn to observe, not interfere.
Watching from afar, I begin to see patterns hidden within its movement.
Observation leads to understanding. Understanding leads to design. The bear's layered fur system provides insulation, waterproofing, and sensory feedback, a multifunctional engineering solution. At the microscopic level, each hair is a hollow tube, providing insulation while minimizing weight.
Thermal imaging reveals how bears regulate temperature across extreme conditions, inspiring insulation design for extreme environments.
The skeletal structure distributes massive loads through perfectly positioned joints and shock-absorbing cartilage.
Material scientists test composites that might replicate the bear's combination of strength, flexibility, and lightweight efficiency. Our prototype integrates multiple systems: structure, actuation, sensors, and power, mimicking biological integration. Stress testing reveals how forces propagate through our design, comparing favorably to nature's proven architecture. Bone-inspired lattice structures reduce weight while maintaining strength, a principle now used in aerospace components.
In motion, the bear's musculature demonstrates efficiency, minimal energy waste, maximum power transfer.
Force analysis reveals how bears minimize impact stress, a principle we're applying to prosthetic limb design.
The retractable claw mechanism demonstrates precision mechanical design, inspiration for adaptive gripping tools. The bear's shoulder joint allows remarkable range of motion while withstanding forces exceeding 2 tons.
Our mechanical analog breaks down into 17 precision components. Nature achieves similar function through integrated biological design.
Precision assembly requires tolerances measured in microns, matching nature's attention to detail.
Strike speed exceeds 40 miles per hour, requiring instant muscle coordination and neural feedback systems.
Coordinating multiple actuators requires sophisticated control algorithms, inspired by neural networks and biological systems. Movement testing reveals efficiency losses in our design, highlighting the sophistication of biological systems.
Paw pads function as natural shock absorbers, a multi-layered system we're still learning to replicate.
Multi-layer shock absorption systems distribute impact forces, reducing wear and improving stability. Gait comparison reveals remaining challenges: nature's fluidity versus our mechanical approximation.
Climbing demonstrates total system integration, strength, balance, and sensory feedback working seamlessly.
With mechanical principles understood, we begin translating nature's solutions into practical engineering designs.
Digital design begins with precise measurements, translating biological curves into manufacturable geometries.
Multiple perspectives reveal subtle design features, each angle informing our engineering approach.
Parametric design allows optimization for specific applications, balancing strength, weight, and manufacturing feasibility.
Material selection balances biological inspiration with practical constraints, cost, availability, and manufacturing capability.
Final digital model represents hundreds of design iterations, ready for prototype fabrication.
Surface texture provides grip without sacrificing durability, inspiring non-slip coating design for robotics.
Advanced manufacturing techniques, 3D metal printing, and precision machining bring digital designs into physical reality.
Design overlay reveals translation accuracy, some features matched precisely, others adapted for mechanical constraints.
Virtual testing predicts performance before physical prototyping, saving time and resources.
With designs finalized and simulations complete, we move to physical prototyping, transforming concept to reality. After careful assembly, the prototype undergoes rigorous testing to ensure reliability and performance. Additive manufacturing builds complex geometries impossible with traditional methods, layer by microscopic layer. Assembly requires patience and precision, each component aligned within micron tolerances.
17 major components integrate into a functional system, each dependent on the others.
First prototype complete, a milestone representing months of research, design, and fabrication. Initial testing proceeds cautiously, validating basic function before advancing to stress tests. Data reveals performance gaps, some expected, others requiring design reconsideration. Iterative refinement addresses weaknesses identified in testing. The engineering process is never truly complete. Design improvements increase efficiency by 12%, incremental gains adding up to significant advancement. Advanced testing environments reveal subtle performance characteristics invisible during basic trials. Nature remains our benchmark, millions of years of testing in the harshest laboratory imaginable. Final prototype represents our best effort at biological mimicry, ready for comprehensive comparison testing. At full stride, the Grizzly reaches 35 miles per hour, combining power with surprising agility.
Our quadruped prototype achieves 20 miles per hour, impressive engineering, yet still outperformed by biology. Side by side, nature's efficiency advantage becomes clear: fluid motion versus mechanical approximation.
Quantitative analysis confirms what observation suggests. Biological systems maintain significant advantages across multiple metrics.
Environmental adaptability requires constant micro-adjustments, sensory feedback loops operating in milliseconds.
Adaptive algorithms improve constantly, yet struggle to match biological responsiveness to novel environments.
Self-repair capabilities remain purely biological. Damaged tissue regenerates without external intervention.
Mechanical systems require skilled maintenance, component replacement, lubrication, periodic calibration. Energy efficiency comparison reveals nature's advantage, achieving more work per unit of energy consumed.
In this moment, millions of years of evolutionary refinement demonstrate engineering excellence we aspire to match.
Comparison reveals how far we've come and how far we have yet to go in matching nature's elegance. Bear-inspired joint designs now lift automotive components, combining strength with precision previously impossible. Search and rescue robotics benefit from all-terrain capability, navigating rubble with bear-like adaptability. Prosthetic design incorporates natural shock absorption, improving comfort and reducing joint stress for users. Applications span industries, from construction to space exploration. Biology inspires engineering solutions. Commercial exoskeletons reduce worker injury by 40%, biomimicry translating to measurable safety improvements. Documented benefits include reduced energy consumption and extended operational lifespan, innovation with economic justifications.
Each application traces back to this living blueprint, nature's designs refined through countless generations.
Future possibilities include planetary exploration robots, bearing-inspired designs conquering alien terrains. Research continues in biomechanics laboratories worldwide, each discovery opening new applications.
Expanding rapidly.
Exactly. Biomimicry requires collaboration, biologists and engineers bridging disciplines to solve complex challenges. Moving forward means respecting our teacher, innovation balanced with conservation responsibility.
We return to where our journey began, the untamed wilderness where nature's engineering continues to evolve. Knowledge passes between generations, not through books, but through observation and experience.
Our responsibility extends beyond learning. Protecting habitats ensures future generations can continue discovering nature's wisdom.
Healthy ecosystems provide endless lessons, each species contributing to nature's engineering school.
In this relationship, nature remains the teacher, humanity the eternal student, learning from perfected designs.
Standing witness to such majesty, we're reminded why preservation matters, for inspiration and for survival.
The future we envision harmonizes technology with nature, not domination, but respectful coexistence.
As the sun sets on our observation, the bear continues its timeless journey, teaching lessons we've only begun to learn.
The journey continues: observe, learn, protect, and innovate. Join us in respecting and preserving nature's engineering genius.
Nature's designs endure, teaching, inspiring, reminding us that the greatest engineering already exists.